Good day. This is video 1 on chapter 5.3. So we're continuing from chapter 5.2 with some more notation. So let R be a rectangle, the product of the two intervals AB cross CD. And this is a rectangle in 2D. And let F be a map from rectangle R to the real numbers, and this map is continuous on the rectangle. Then we're going to say that the double integral of f over r dA can be written in two ways. It can be written as the integral from a to b, the integral from c to d of f dy dx, or the integral from c to d, the integral from a to b, f dx dy. Now you might ask, why these two different new notations? Well, the one in the middle, we are saying x is starting at a and x is ending at b, and y is starting at c and y is ending at d. Now if you look at the last one, we are saying y is starting at c and y is ending at d, or x is starting at a and x is ending at b. So we can either start from x on the outside and then y, or start from y on the outside and then x. So the last two forms are known as iterated integrals because we pick an order, maybe dy then dx or dx dy, and the first one is known as a double integral. Now for iterated integrals we must work from the inside to the outside, and you can see example 138, or in an example I will do shortly. Now as a bit of warning, sometimes improper integrals make an appearance. So remember we did improper integrals in 1 to 4, so please do example 139 in the notes. I'm not going to do that in today's video. Alright, so let's do an example to evaluate a double integral over a rectangle. So I have the double integral 3x squared plus 2xy over rectangle D, and D is a rectangle 1, 2 cross 0, 2. So we are going to calculate this double integral. Now first of all, D is closed and bounded, and this is a continuous function on D, so we know that this function is indeed integral over D, so we know it exists, and so now we just got to find this value. And we can do this in two ways. So we know we have the two iterated integrals. So let's start with the first one. So let's call this way 1. So we're going to write this as the integral. X is starting from 1, ending at 2. Y is starting from 0, ending at 2. And the function is 3x squared plus 2xy. And then it is dy dx. So x started from 1 to 2, and y is from 0 to 2. And then what you do is you work from the inside to the outside. So you take the integrand and you integrate this with respect to y, treating x as a constant. So if you do this, you get 3x squared y, plus if you integrate that, that becomes xy squared. And as before, you draw a vertical line. The top bound is 2 and the bottom bound is 0, and it's an integral from 1 to 2 dx. And we are happy because if you do partial y of 3x squared y plus xy squared, that is indeed equal to 3x squared plus 2xy. So that's what you do. So you work from the inside to the outside. And now what you do is you plug in 2. So you replace all the y's with 2. So if you replace that y with 2, so it becomes 6x squared plus that y with 2, that becomes 4x. Then you replace all the y's with 0, it becomes 0 dx. And now it becomes the integral from 1 to 2 of 6x squared plus 4x dx. And now it's a first year problem. If we integrate that, that becomes x to the power 3. So it's going to be 2x to the power 3. If we integrate that, that becomes 2x squared. And using the FTC, top bound is 2 and the bottom bound is 1. You can see if you differentiate that, you get that. If you differentiate that, you get that. Great. And so now, if I plug in 2, I get 24. And if I plug in 1, I get 4. So the numerical value for this double integral is 20. So this is treating this double integral as an iterated integral in the order dy dx. However, we can also do this in a second way. So by changing the order of integration, we can now say it's an integral from 0 to 2, then an integral from 1 to 2. The function is still 3x squared plus 2xy, but now the order is dx dy, because y ranges with values from 0 to 2 and x ranges from value from 1 to 2. Great. So now, as before, we start from the inside, but this time around we integrate with respect to x, treating y as a constant. So if we integrate with respect to x, now it becomes x cubed, because the derivative of x cubed is 3x squared, and if you integrate that, that now becomes x squared y. And now we draw a line. The top bound is 2 and the bottom bound is 1 dy. So because we have dy there, we know we're replacing all the x's with 1 and all the x's with 2. And so we continue. We replace all the x's with 2, so that becomes 8 plus 4y. And then we replace all the x's with 1, so it becomes 1 plus y. And if we simplify that, that becomes 8 minus 1, which is 7, plus 3y dy. So now, in my second method, it becomes a first year problem all in terms of y. So I integrate 7, so that's 7y over 2, and sorry about that, the integral of 7 is obviously, I'm sure you spotted it, it's 7y, and that integral is 3y over 2. And by the FTC, you draw a line, the top bound is 2 and the bottom bound is 0. And so now, as before, I replace all the y's with 2, so I get 14 plus, so the integral of 3y is 3y squared over 2, so if I replace y with 2, so it becomes 14 plus 6, and if I replace all the y's with 0, so it's 0 plus 0. And what do you know? We also got the value of 20. So we see whether we treat it as an integral, an iterated integral in the order dy dx or dx dy, in both methods we got the value of 20. So that's pretty cool. So this is how you evaluated double integrals over a rectangle. So you just go pick a good order and then you just integrate, and remember, as you've seen here, you start from the inside to the outside. That is the lesson to be learned from this example. Alright, but there's more to be done. Great. So what I want to do now is look at two types of regions. So there are lots of regions out there over which you can integrate, which is not necessarily a rectangle. And so we're going to start with region type 1. So if you look at region type 1, we can do vertical slices. So if you look at type 1, it's all of the blue, the shaded blue area. So if you look at the shaded blue area, it is all the points, all the 2D vectors xy. So D is a subset of R2, so it's all the 2D vectors where x is from A to B, because we slice from left to right. And we can see that if we slice it, this x starts at A and x ends at B. But now, if you take a specific slice, this is where it starts and this is where it ends. So if you take another vertical slice, it starts here and it ends here. And you can see all of the starting points lie on the same curve, which is y is equal to g1x, and all the ending points lie on the same curve, y is equal to g2x. So you see that y values lie between the two curves. So if this happens, this is called type 1. And then theorem 141 says that if it's closed and bounded and good things happen, that the double integral of f over d can be written as a specific iterated integral where the order matters. So x starts at A and x ends at B. And y starts on the curve g1x and y ends on the curve g2x. So this is type 1 because if you make vertical slices, all of the starting points lie on the same curve and all the ending points lie on the same curve. And this is how you would evaluate this double integral. So this is type 1, where we make vertical slices of the region. Now let's have a look at type 2. Now for type 2, we are now going to make horizontal slices. So for type 2, we are making horizontal slices, so from left to right. So we're making horizontal slices. So if you look at type 2 carefully, you can see that is all the 2D vectors x, y, where the y values are between C and D. But now, if you make a horizontal slice, that will be the starting point, that will be the ending point. So you only want that bit because that is in the blue region. Or if you make another horizontal slice, this is the starting point and this is the ending point. And you can see all of the starting points lie on the equation x equal to h1y, and all the ending points lie on the equation x is h2y. So you can see the x values are bounded between curve 1 and curve 2. So we say D is the region, all of the 2D vectors x, y, where y is between C and D, and x lies between curve 1 and curve 2. So we say that x is between h1y and h2y. So this is type 2. So how do we do a double integral over type 2? Well, then we say the double integral of f over d is the following iterated integral. Y starts at C and y ends at D. X starts at h1y and x ends at h2y, and the integrand is still fxy. So if it's type 2, then you see that the middle one is in terms of y. And if it's type 1, you see that the second integral is in terms of x. However, you see in both cases that the first integral that you write down have to have numbers. So the type 1 was the integral from a to b, and this one is the integral from c to d. So notation really matters. So make sure if you do these questions that depending whether it's type 1 or type 2, that you write the double integral correctly as an iterated integral with the correct order and with the correct bounds. Alright? And this is part of my remark. Order and bound matters for iterated integrals. Sometimes a problem can be of type 1 and type 2. You will see some examples. Or you can use combinations of type 1 and or type 2. Alright? But again, I want to emphasize here, notation matters, the order matters, and the bound matters. Alright? So please draw pictures so that you are clear over which region you are integrating. Alright, so I have 3 examples for us to look at. So let's start with example 1, which is example 143 in the textbook. Let D be the region bounded by the line with equations y equals minus x over 2 and a parabola with equation x equals y squared minus 3. Draw it, and we want to know what type this is. Now, this is a straight line, so we know how to draw straight lines, and this is a parabola, we know how to draw parabola, but we want the region bounded between these two curves. So the very first thing we need to do is, when do y equal to minus x over 2 and x equal to y squared minus 3 intersect? So that calculation is necessary. So I'm going to leave that calculation for you, but if you do the calculation, you will see they cut at points 6 minus 3 and minus 2, 1. So please do this calculation and that you agree with my calculation. Alright, so now we can draw this. So x-axis, y-axis. So the line y is minus x over 2 is a line that goes through the origin that looks like that. X equal to y squared minus 3 is the parabola that looks like that. So you would have calculated this is the point 6 minus 3, and this is the point minus 2, 1. And so this is the region, that D, that we care about, because the one boundary is the straight line and the other boundary is the parabola. Now we've drawn it, and now they're asking us what type is this? Is this type 1 or is this type 2? Now, if you draw this vertical line, then you can see the starting point is on the parabola and the ending point is on the parabola. But if you draw this vertical line, then you can see the starting point is on the parabola, but the ending point is on the straight line. So you see, as you make vertical slices, that the starting points are always on the parabola, but the ending point may be on different curves. Sometimes it's on the parabola, sometimes it's on the straight line. So this is not using vertical slices. So this is not type 1. So let's have a look if it is of type 2. So let's make horizontal slices. So if I make a horizontal slice, it starts on the parabola and it ends on the straight line. If I make another horizontal slice, it starts on the parabola and it ends on the straight line. If I make another horizontal line, it starts on the parabola and it ends on the straight line. So this is type 2. So using horizontal slices, it always starts on the parabola and it always ends on the straight line. So here using a ruler is a really good idea. And now let's do part B. We want to write this as an iterated integral. Again, as I said before, order matters, notation matters, and the bound matters. Alright? So this is why it is sometimes when you can, you draw it. So the integral will be, so because we are making horizontal slices, we can see what is the smallest y value we get? That's minus 3. And the biggest y value, we get 1. So the outer bound would be dy. The integrand is y e to the x. So that we can't change. The integrand is y times e to the x. And so the one before it should be dx. And so now we need to know x starts on the parabola. And so the equation of the parabola, x equal to y squared minus 3. So this is y squared minus 3. And where does x end? X end on the straight line. So we have y equals minus x over 2. So we get 2y equals minus x. And so we get x equals minus 2y. So we get minus 2y. So we see the integral, if you want to write it as an iterated integral, is the integral from minus 3 to 1, the integral from y squared minus 3 to minus 2y, the integrand, which is y e to the x, then dx dy. And this is it written as an iterated integral. And now the next part is calculated. So I want you to do it and see, do you get the answer that is minus 5e minus 2 plus 3e to the 6 over 4. If you get stuck, read page 129. And this is our first example. So you can see the region over which we integrated was no longer a rectangle. It was a region bounded by a parabola and a straight line. So turning this into an iterated integral, and you will do the calculation. So step 1, you've got to turn this correctly into an iterated integral. After doing that, you can now do the calculation and see what is the numerical value of this double integral. Heaps of fun, so please do this. Alright, you don't want to miss out on all these fun calculations. Great. Now let's have a look at our second example. So our second example, the region is a triangle. So T is the triangle with vertices 0, 0, 1, 1, 0, 2. Draw it. There is the diagram. So there is a diagram of the region over which we're integrating. And I want to know which type is it. Is it type 1 or is it type 2? Now, if we draw a horizontal line, it starts there and it ends there on that straight line. But if I draw this horizontal line, it starts on the y-axis, but now it ends on a different curve. So this is not type 2, where we make horizontal slices. This time around, we are making vertical slices. So if we make a vertical slice, it starts there and it ends there. If we make another vertical slice, it starts there and it ends there. If we make another vertical slice, it starts there and it ends there. So you see, it always starts on line L1 and it always ends on line L2. So we've drawn it, and which type is it? It is now of type 1, because now we can make vertical slices. And now in part B, we want to calculate the double integral of xy over this region D, which is now a triangle. Great. So we got it. This is of type 1. So we first turn this into an iterated integral. So this is a very important step. So by making vertical slices, we see the x value starts at 0 and ending at 1. And then the one before it should be dy, and this is xy. And so it starts on the equation of line 1. So if you do the calculation, the equation of line 1 is y is equal to x, and the equation of line 2 is y is equal to 2 minus x. I'm leaving this for you to check. So if I make a vertical slice, where does x start? X starts when x equals y. And where does x end? X end when it's equal to 2 minus, very important, this must be in terms of x. So this point, y ends when it's y starts when it's equal to x. Getting tongue twisted here. So y start when it's equal to x, and y ends when it's equal to 2 minus x. So that's when y end when it's equal to 2 minus x. So this is 2 minus x. So because you have the outer bound is dx, so the outer differential is dx, this and this must be in terms of x. So don't get lost in the notation. This is how you convert this into an iterated integral if it's of type 1. And now let's quickly do the calculation. So please pause and maybe do it and check that you agree with my answer. So first I integrate with respect to y. So from the inside to the outside. So this becomes xy squared over 2, plugging in 2 minus x, plugging in x, dx. So we want to see that you know the integral of xy is xy squared over 2. So integrating with respect to y, keeping x as a constant. And now you replace all the y's with 2 minus x squared over 2, and then it's x times x squared over 2. And don't forget the dx. And if you do this calculation, it simplifies to 2x minus 2x squared dx. And then it's a first year problem. We integrate 2x, that's x squared. We integrate that, which is 2/3 x cubed. By the FTC, we plug in 1 and 0. If I plug in 1, I get 1. If I plug in 1 there, I get 2/3. So 1 minus 2/3 is a third, minus 0. So the numerical value for this double integral is a third. And that is the answer to part B. So we have now found it as a double integral over the region D, which is a triangle of xy. But in part C, they're asking us a strange question. Can you change the order of integration? So can you change the order of integration? So can you treat this as a type 2 problem? Well, the trick here is to use a theorem from chapter 5.2. So what we're going to do is we are going to split up the region into 2 parts. So we're going to have region D1, which is the bottom half of the triangle. So from 0, 0 to the point 1, 1. And then we're going to have the top half of the triangle. So from 1, 1 to the point 0, 2. So this is D1 and this is D2. So the region is D1 union D2. So if you take all of those blue points plus all of those blue points and you put those two sets together, you get set D. Now, why do we do this? Because now if we do a horizontal line, then you see it starts there and it ends there. It starts there and it ends there. So everywhere on D1, it starts and ends at the same places. And if you look at region D2, the starts is the same places and the ends are on the same curve. So we can treat this as a type 2, but we now have to be careful and divide the region up into two parts. So now we're going to have two iterated integrals. So we can now say the integral becomes the following. So for this part, it's a double integral, and if we do these horizontal slices, y starts at 0 and y ends at 1. And then we got to work out where does x start and where does x end. And remember, the function doesn't change, it's still xy. So here, if you look at this carefully, where does x start? X starts at this point where the y value is 0. So here, it starts at this point where x is equal to 0. So x equal to 0, this is the curve where the starts are. It ends here, and so this is the curve x equal to y. So it starts here on this curve when x equal to y. So for D1, x start equals 0 and x end equal to y. And so the bottom bound here is 0 and the top bound there is y. And that is now treating D1. Now we got to treat D2. And so if you look at D2, if we do horizontal slices, the smallest y value is 1 and the biggest y value is 2. So the y ranges from 1 to 2. So that's dy. And now if you look at the x's, so again, looking at the x's, we got to look carefully. Where does x start? X starts at, the function is still xy. X starts at the value 0, and now it ends on this curve. And the equation of this curve is x is 2 minus y. So this is 2 minus y. And now you have written it as a sum of two iterated integrals. And I'm going to leave it for you as homework, that when you calculate this value plus this value and you add this up, do you also get a third? So this is an interesting example. So do give this one a go. Alright, but I saved the best for last. And the best for last is this little problem, where D is a triangle again, but this time around the vertices are 0, 0, 1, 0, 1, 2. And we want to evaluate the double integral of the function cos pi x squared dA, this double integral over this triangle, over this region D. So my first remark is, this is both of type 1 and type 2. So you can make vertical slices and the starting curves and the ending curves are the same, or you can make horizontal slices and the starting curves and the ending curves are the same. So we, like the question we started off today, is we have possibly two ways that we can solve this question. So let's start off by looking at making horizontal slices. So making horizontal slices, then we can say that the integral equals, so if we make horizontal slices, where do we start? The smallest y value we can get is 0, and the biggest y value we can get is 2. And then the function, the integrand is cos pi x squared. And so now this is the line y equal to 2x, leaving it for you to verify. And this is the line when x equal to 1. So here we got to have, where does x start? So it starts here. It starts here when it is y over 2. And where does x end? X end when it is equal to 1. So this is if we treat it by making horizontal slices. If we write it as an integral and we have an iterated integral of the order dy dx, then we are making vertical slices. And we can see the smallest x value is 0 and the biggest x value is 1. So x starts at 0, x ends at 1. So if we make slices, where do we start? So the y value starts at 0. And where does the y value end? The y value ends on that curve, which is given by y ends at 2x. So this must be in terms of x, and this must be in terms of x. So we have two choices. So any one of the two iterated integrals we have to calculate. However, now let's try the first one. So looking at the first one, we need to integrate cos pi x squared dx. But does it look familiar? The answer is no. And even if you try it with a technique like integration by parts, you will get stuck, even more stuck, etc. So when you get stuck and you realize that maybe treating it as an iterated integral in this order dx dy, and you get stuck and you continue to get stuck, then you say, alright, let's try something else. So the first one is not the way to go. This is not the way to go. So let's see. So do try this at home and do see truly how stuck you can get trying that order. Alright, so let's try the second order. So the second order is the integral from 0 to 1, the integral from 0 to 2x cos pi x squared dy dx. Now if you look at the integrand, no y appears. So that is pretty cool, because then it's very easy to integrate. So all that you do is, it's like integrating 1. The integral of 1 with respect to y becomes y cos pi x squared, and the bottom bound is 0 and the top bound is 2x dx. So now what you do is you replace all the y's with 2x, so that becomes 2x cos pi x squared, and you replace y with 0, so you get minus 0, so you end up getting all of this. So now we get an integral from 0 to 1 of 2x cos pi x squared dx. So now it's a first year question, and because it's a first year question, you've got to remember all of the techniques from first year, like integration by parts, partial fractions, maybe substitution, using partial fractions. All of the techniques from first year can appear in the exam. So how I'm going to solve this question, I'm going to do the following. I am going to say the following. Let u equal to pi x squared. So u is a function of x, so the derivative of u with respect to x becomes 2 pi x. And so by rearranging, I get du is 2 pi x dx, and so I get that 2x dx is du over pi. Alright, now we are interested in doing the integral from 0 to 1 of cos pi x squared of 2x dx. Now you see, if I do this substitution, this bit becomes du over pi, this bit becomes cos u, and remember, this is a definite integral. So if you do integration by parts, you also have to work out the new bounds. So you need to say, if x equal to 0, then u equal to pi times 0 squared, which is pi. Pi times 0 squared, it is equal to 0. This is when if x equal to 1, then u equal to pi times 1 squared, which is pi. Alright, so if we use integration by parts, this now becomes an integral from 0 to pi. That becomes cos u, and this becomes du over pi. So integration by parts did work here, because the problem was purely in terms of x, now it's purely in terms of u. And now we proceed. The integral of cos u, that is sine u over pi, plug in 0 and pi. And so now we proceed. We will then have sine pi over pi minus sine 0 over pi. Sine pi is 0, so this becomes 0. Sine 0 is 0, so it's 0 minus 0, and that's equal to 0. Alright? And that, ladies and gentlemen, is the answer to this question. So we saw that here, if you treat it as an iterated integral in one order, you would get stuck. So one order, you get stuck. So one order, you get stuck. But if you are brave and do a different order, it is actually a very easy problem. It works. So the moral of the lesson here is, if method 1 doesn't work, do try another method. And that, ladies and gentlemen, is the end of the video. I hope you've enjoyed this video. So please stay tuned for part 2 coming soon. Good day.